Hello, in this video we're going to continue talking about what electrons are doing in atoms, and specifically, now that we've mentioned what quantum numbers are part of the solutions of the Schrodinger equation for an atom, we're going to look at what those quantum numbers correspond to and what the electrons are doing inside of the nucleus. So I have here a figure we're going to look at in quite a bit of detail in this video, and also just a reminder that one of the quantum numbers we care about is L, the angular momentum quantum number, and that primarily tells us shape. And just again as a reminder, we are looking at L can be equal to 0, 1, 2, and it goes up to n minus 1, based on that principal quantum number. We are primarily going to look at these three values of L. L equals 1, 0, 1, and 2. L can be higher than that, but we're not going to look at the f orbitals in this class, because mostly we're focused on these L equals 0, 1, and 2 that are involved in chemical bonding that we're going to look at in the next few chapters. And now, just as a reminder, there's a letter designation that goes with these orbitals, with this quantum number. So a L equals 0 orbital is known as an s orbital, an L equals 1 is known as a p orbital, and an L equals 2 is known as a d orbital. So these have specific labels, and again, that the higher than that, there are also letters to go with those, but we're mostly going to focus on these. And one thing I just want to mention that I haven't brought up yet to this point is that we talk about these orbitals as being shells. You can think of these as the electrons are sort of forming a shell around the nucleus. And we think about these shells as belonging to specific values of the principal quantum number n. So we have the n equals 1 shell, the n equals 2 shell, etc. n equals 3 shell, and we can continue that. And the different values of L are known as subshells. So if you have n equals 1, there's an L equals 0, or S, subshell. For n equals 2, we can have a value of L is equal to 0 or 1. And so we have two different subshells that go with the n equals 2. And this n equals 1, L equals 0 subshell we would call a 1s orbital. And for n equals 2, we have an L equals 0 is a possibility, so that's another s. Or we can have L equals 1, which we call a p orbital. And these subshells would be the 2s subshell and the 2p subshell. Now, the 2p subshell consists of three orbitals because we have different values of m sub L, that magnetic quantum number. So this is a little bit of review from the previous video. So for our 2p orbital, there are three of them, and in the next couple of videos, we'll look at what those look like. For the rest of this video, we're going to focus in on specifically the L equals 0 s orbitals of different subshells, right? So we can have 1s or 2s or 3s. These are, again, labeled by their principal quantum number. But only one possible value of m sub L, because m sub L goes from negative L through 0 to positive L with all the integers in between. So, but in the case of a L equals 0, m sub L equals 0, and so there's always only one s orbital per shell. So for each value of n, there's one s orbital. There's a single s orbital that goes with it. So n equals 1, you have the 1s orbital. N equals 2, you have the 2s orbital, and et cetera, et cetera. What do these orbitals look like? So if you remember, we have these mathematical solutions to this Schrodinger equation, this psi, this wave function. And what we usually look at is, again, the square of this wave function tells us about probability. And specifically for the s orbitals, they look like this. And these are a few different ways of representing our s orbitals here. So one is just to look at the plot of psi squared as a function of distance from the nucleus. So we're taking our, so that's sort of going along with this down here. We're taking our 0 point to be here right in the middle of the atom, and our r, our distance from the nucleus, we call r, is just how far apart our radius of this as we spread out. And so we see the value of psi squared is very large, close to the nucleus, and decreases exponentially as we go further away from the nucleus. But what this doesn't take into account is that the amount of volume you have close to the nucleus is very small. So even though the value of psi squared, the probability is very high there, there's not a lot of space for that electron to be. And so this other plot here, this what's called the radial distribution function, takes into account the fact that these sort of layers of the atom take up different amount of volume. So even though the value of psi squared is very high, close to the nucleus, there's not a lot of space for that electron to be within that. And so right at the nucleus it goes to 0 because there's no space there if you go down to a small point right at the nucleus. But the value goes up and increases because there's more space for that to be. But as the value of that probability decreases, you get some maximum here, and then it decreases exponentially. So this is sort of our one other thing that's important about this is that this is the same in all directions. So an s orbital is shaped like a ball. And that's what this picture here is depicting. This is how we'll often look at orbitals, is in this D section here. This is what's called, let me get the name of this right, a boundary surface. There we go. And what this represents is what's the surface that contains 90% of the probability. You can pick this to be whatever you want, but usually this is done at 90%. So there's a 90% chance to find the electron within that specific shape that's shown. So we would pick some distance here. 90% is going to be something like this, and we draw the shape of the orbital that goes with that. So what are the key takeaways from this? One is that s orbitals are spherical. Let's give myself some space to do this on the side over here. So we'll move these over here. And our takeaways are, for s orbitals, they are spherical. There's only one per shell, because we have the only one possible m sub L value. So m sub L has to equal 0 if L equals 0. And one other thing that we haven't talked about yet, that is also true for s orbitals and other orbitals, is that the principal quantum number, so n, tells us energy. So as we increase n, the energy of the orbital gets higher. But it also tells us about size. So let's take a look at what the size of different s orbitals look like. And we'll look at that in the next video.